Okay, so we move on to Florian Bauer. Still flying.
There might be some drone footage.
I guess we're going to change from presentation now.
Yeah, good afternoon, everybody. My name is Florian from Kitekraft, and I'm here to give you an update on our progress of the past 2 years approximately. And I have a video here, so for those who don't know our system, so we have now this beautiful ground station with all the electronic cabinets and also with the grid connection. The kite launches from the ground station, the winch is releasing it, and it's completely automatically, so we just push the button, please land, please launch now, and then push another button, please land now. And of course, it's a matter of simple automation to just make this dependent on the wind speed. And once the kite is hovered out with the full tether length, it launches into the figure 8 flight. And then, of course, it's also propelled by the wind and we can produce power. And then at one point, once we want to land the kite again, it simply goes back to hovering, which should happen on the right side of the figure 8 now. And as you also know, it's a flight chain system, so we use the onboard rotors at the moment as wind turbines. We transmit the power over 800 volt DC in a tether. The tether has a diameter of 6 millimeters approximately. And there you see how the ground station now catches again the tether and how we winch it back to the ground station. And then the kite has like hooks, so we simply pull it against the ground station and then we reduce the thrust and it then simply hangs on the ground station. As said, fully automatic. We have these 8 rotors. We have flaps on the main wing. We have the electric mechanical tether, so there's full 20 kilowatts approximately power transmission between the kite and the ground station. Then on the ground station, we have this landing hooks, we have a wind sensor, of course, and as I already put it here, redundancy everywhere, so you see there are 3 wind sensors. We have the same on the kite, and the goal is to have no single point of failure, even in the tether. For that, I presented on the AVAC 4 years ago already, how we do that. So we can even have a short circuit in the tether, and we lose only 2 rotors, and with the remaining 6 rotors, we can still fly without a battery on board. And yeah, some recent achievements. So maybe first of all, about a year and a half ago, we moved from the TU Munich to our own offices. We have now a nice office, 400 square meters of machine hall. And this is an image of the recent wind tunnel tests. And one of the challenges that we face is when we are hovering, we are at 90 degrees angle of attack. And then, of course, the wing is completely stalled. And we use the flaps and the prop wash to get control authority about the vertical axis. So this is what Mechanics kite actually killed. So that's why they lost the kite offshore, for example. And it works super nicely if there's little wind or no wind. And we wanted to see here in the wind tunnel, how does this behave if we have wind? And here you see it, for example, at 10 meters per second, and you see with this smoke that the prop wash is still pushing over the wing, and with changing the flaps, we still have enough control authority. So this was a really nice proof, really nice validation. And we actually also hovered the kite in that wind tunnel afterwards. So we then pushed with 20 meters of second wind, and the kite was actually hovering in that wind tunnel. So maybe the very first time at all that something was flying in that wind tunnel. Another recent achievement, we now clocked more than 100 undockings and dockings onto and from the ground station. And yeah, we are now, of course, flying more and more. And yeah, this is one of the biggest achievements. We invited people there. We on our test site, which is south of Munich. For example, on the bottom left, you see the mayor of Oberhaching giving a speech. And it was really amazing to see all the enthusiasm of the local people. They were really proud, for example, that we are testing this new technology there in their village. Then also the boss of the Bayernwerk, so the local grid operator, department, he was really lucky that we connected our airborne wind energy system for the first time at their area, and it was really a nice event. So at that event, we really simply plugged in and did nothing more than that. In the afternoon, we did then some hover test, but it was a few weeks later when we then first did the entire flight. And there we did this all-phase flight, and at the end I have the video of that. And we also pushed a little bit of power into the grid even. And what you see here is our mobile ground station again, and there's actually the transformer station at the village. So we have a DC cable now going from that transformer station and from our grid inverter cabinet, which is, by the way, from Siemens. Maybe I should mention that as well. So we got a lot of help from Bayernwerk, of course, a lot of help from Siemens. We have Siemens inverters there, and this works really nicely. So the very first time we plugged it in, it worked right away, and we could take the full 30 kilowatts out of the net, and we could push the full 30 kilowatts back into the grid with 100 milliseconds of change. Our focus so far has been the development of the scalable, industrializable, and fully automatic airborne wind energy concept. And the business model works only if we go to 100 kilowatt to multi-megawatt, if it is industrial grade and fully automatic. So this is where I actually started from my PhD thesis, and that's why we came up to the drag power principle. So we have the generators on board. We believe and still believe that this is the best way to go on with airborne wind energy. We have this box plane kite to identify to fulfill those requirements. And at the moment, the focus is still on a small-scale technology demonstrator, especially the fully automatic flight. I also want to mention we never had a joystick to manually control the kite. We always, from the beginning, had just push buttons to have minimal crew and pilot interactions. And the advantage of this small-scale concept is, a small-scale demonstrator, is that we can validate the entire concept, especially including the sensor, actuator, communication software setup, and the dance of the kite with the ground station. So there's some interesting dynamics, of course. For example, who's controlling actually the tether tension, who's controlling the position of the kite during that winching in and winching out. And that's something that you see in our videos that we solved quite nicely. So achievements for that is that we uncovered no roadblocks, and so far the concept is evaluated positively. But there's one shortcoming. This kite cannot really generate an efficient power curve. But this is what we knew from the very beginning when we did just studies on that. But a good thing is that efficiency simply comes with upscaling, just making it bigger, keeping the same airfoil, for example, having the same efficiencies on the powertrains or the same voltage, for example. So we really have to just build it bigger, and then we get the efficiency. Yeah, some product development principles, also something that I said in the last ARVIC. The best part is no part. That's from Elon Musk. The best process is no process. And we always ask, can we make it simpler? And during all those testings, we learned a lot. So for example, shortly, or when we dock to the ground station, we need quite exactly the altitude, because the hooks are either then too high or too low if we don't know that. And we started to implement RTK, so GPS-based RTK with real-time kinematics. So you have a GPS sensor also on the ground station, and then you get these atmospheric disturbances out. And it's really amazing. So we bought this simply from Make Sense, and it worked also right away. And we knew then really the position exactly by 1 centimeters. But then we figured out a little bit later, wait a minute, we have actually line angle sensors on the kite already. We know, of course, the orientation of the kite. And if we shortly before the ground station, the tether is straight. So we also get, by simple equations, the altitude of the kite in centimeter accuracy, so we do not need GPS actually. And that's also important for the product development, because there could be GPS-denied airspaces. There could be somebody with a GPS spoofer or a GPS jammer, which then take down the kites, or a kite farm, which would be not super nice, of course. So those are also the learnings and the developments that we are integrating right now with this small scale system that we can really nicely then see and validate in real life with a really cheap and small scale system before we test it in the large scale. Yeah, design, assume the ideas designs are wrong to some extent, so we design, simulate, test and build. And we try to make all possible painful learnings fast at small scale and at low cost. One of the really nice things that we have is our C++ based systems engineering framework process. So we try to get everything in C++, so we have the same programming language for the modeling, for the designs, and then also the same exact control algorithms run on the kite, on the microcontrollers, and on the ground station as well. So we have a Linux computer on the ground station, Linux computer on the kite. We have the microcontrollers on the kite, microcontrollers on the ground station. Each communicate with the same C++ framework, and we can validate all of that really nicely on our laptops, which is simply running a normal Linux environment. And here's some telemetry data for an entire flight. So you see, maybe I go here, speak a little bit louder. So the kite launches here on the ground station. There we start at the moment with one calibration run, where the ground station simply calibrates 1 times 360 degrees, while the kite is still hanging on it. So this helps, for example, for magnetometers, GPS, and so on. Then we hover up, the kite then pulls out the tether, the winch releases it, and then at this point we are just before the transitioning, then we transition into the figure-8 flight, then we fly a few figures of 8, and then at one point when we want to land the kite again, you see that here the kite simply basically stops in the air. And we do that by using the onboard rotors really hard as wind turbines then, and also get all the flaps up, so the kite really has no glide ratio anymore, and it literally stops in the air and gets to hovering. Then we hover slowly down. The ground station then engages again to guide the tether, and then we pull it back. Oh yeah, I also have labels here. One other example, and this is shortly after undocking, and here you see some data, for example, the barometer, and there you can also see the barometer is not really accurate. Then we have LiDAR, but the problem, and LiDAR here means that we have a LiDAR mounted on the kite, which looks down and measures the altitude of the kite. But the problem is if you have a cornfield there, then you measure between the corn or on the top, or let's say you fly out, you fly a few figures of 8, there's snow then falling, and then you measure something completely different. So we also figured out LiDAR is inherently unsafe, so we will not be able to use it in the product. Then we have RDK, and you see RDK is super exact. And then we also have what I just told in green, the gimbal on the orientation, which is also super nice, up to around 5 meters of tether length. Yeah, there's again the graphical user interface of our C++ simulation framework. Another nice thing is that we can also integrate the graphical user interface there. It's written in Qt. Which is an open source library, and you can also see there that we have now implemented wind fields with turbulence, so to really simulate quite exactly what is going on there. One other effort is to get to the BVLOS permit, so that nobody has to be on site anymore, ideally. So that's what we applied for. But on the way there, of course, it also just simplifies the operations. That just some pilot needs to be there, needs to sit there, look at the data, of course, be ready to push a button, but to really minimize the efforts of the flight. But already today, it's pretty minimal. So we just need 2 people to observe a flight. One is looking at data, giving comments, and another one is a visual observer. Some conclusions. What you have achieved is Kitekraft achieved all-phase automatic flight with grid connection. We have simulative and flight test results that serve as concept validation, which is now ready for upscaling. So this is what we will do over the next months to really design and optimize the 100 kilowatt product, which has then around 10 meters of wingspan, 10 to 12 meters wingspan. Right, that's what I was just saying. And then we still continue flight testing with the small scale system, because the sensor setup, the communication setup, the Linux computer shall be exactly the same. It shall be just a little bit bigger. So we really want to take the learnings and just make it a little bit bigger. But the beauty of our box plane should be that it should still behave like a perfect rigid body. So there will be really no changes in the control. And then, of course, I actually hope that I can announce that we already got it now, but it should be any day now that we get the BVLOS permit from LBA. And thank you very much. I can now take questions, while in the background I also keep the video rolling.
Okay. Thank you very much, Florian. We have time for a couple of questions. Maybe you want the microphone.
In the meantime, I have a quick question. What voltage do you use in the tether?
One question is, what voltage do we have in a tether? It's 800 volt at the moment. But we also have plans to go up to 1.5 kilovolts, which is more or less the standard also in photovoltaics at the moment.
Thank you, Florian. Very impressive. One question. Can you say something about the noise the system makes when it's flying?
Yeah, also excellent question. When I did this comparison between the different technologies in my PhD, there was one question mark, and that's exactly the noise. I would say it's still a little bit of a question mark, but we figured that the rotors, of course, make the highest noise, but we have a lot of design freedom. So, for example, we can add more rotor blades, and it suddenly gets even more efficient and way less noisy. So right now we have a 6-blade rotor, which is still off the shelf, constructed from 2-blade rotors. So it's really that prototypey, but still in a distance of 200 meters, you don't hear anything when the kite is hovering. During power production, you still hear something, but this is also because the control parameters that we use for the moment. So, for example, if the kite detects it might be going too low, then we give full thrust, and then of course you hear that change. But if you're in power generation, the rotors are actually running slower than during hovering, so it is also then lower noise.
Okay. Well, very fast, last question.
Why do we not use pitot tubes for the measurement on the kite, and why are we using LiDAR? So the LiDAR is really just pointing down to measure the altitude. So it's not for measuring the wind. And at the moment, we actually do have a pitot tube to measure the airspeed, but we want to get rid of it. So as I said yesterday, the work from Oriole, for example, with the extended Kalman filter to get rid of this is really excellent. Because it's simply just a question of time once it's clocked, and as I said, the best part is no part.
I got myself a question, Florian. Nicole from Enerkite was targeting 10 cents per kilowatt hour as LCOE. Do you have any similar number for your product?
Yeah, that's also what we are targeting. And actually the local utility, municipal utility in Oberhaching, where our test site is, they offer us 12 cents per kilowatt hour.
Okay, thank you. Okay, thank you very much. We move on.